All right, moving on. You could take a phone break if you wanted. You just have to pause me, right? All right, redox reactions are spontaneous only in one direction. We saw this earlier, but when zinc sees copper 2, it could be oxidized to zinc 2 and copper solid. When copper sees zinc 2, you go the other way. So these are reverse reactions of each other, right? And the question is, what happens? Does this reaction happen or does this reaction happen? Okay, so if we put these things together, if a spontaneous reaction happens, we should see something happen. If something happens here, I expect to see this guy get covered with solid copper, right? Which turns out it looks kind of black. It doesn't really look nice and coppery. If this one works, I should see the copper plated with nice silver zinc. Let's see which one we see. And it's this one. So zinc is oxidized and copper is reduced. Copper doesn't want to be oxidized and zinc doesn't want to be reduced. Redox reactions can go only one direction, right? Different compounds, different atoms, ions, have different, oh, I lost my words. They want to be oxidized or reduced, right? They have a different potential to do that. And what we do then is you can actually tabulate this. So table 1 is a table of standard reduction potentials. Right, and you can see that's written E, not red. This means standard reduction potential, and it's in volts. All right. We've seen this standard thing before, standard conditions. In this case, the standard conditions are considered 1 molar in whatever we're talking about, or 1 bar, which is a pressure, and 25 degrees Celsius. All right. We can also have oxidation potentials. We'll talk about that in 1 second. If you look at all these reactions, these half reactions, they are all reduction half reactions. Chlorine goes from 0 to -2. Oxygen goes from 0 to -2. They're all being reduced. And the way we look at this, the standard reduction potential, right, given this plus 1.36 volts or negative 3.04 volts, this tells me how much it wants to be reduced. A positive number means it wants to be reduced. A negative number means it doesn't. All right, and the way this table is built is you compare each of these compounds to the hydrogen electrode, the standard hydrogen electrode, right? And it's defined as having a potential of 0. So if you give him 0 and you make him 1 half reaction, the other guy the other half reaction, you can measure these using your voltmeter. All right, so a positive potential means it wants to go that way. A negative means it doesn't. A bigger positive means more. So this wants to be more, wants to be reduced more than iron 3 does. This is how we read it. All right, so go through this. Notes, potentials are intensive properties. So what that means is the stoichiometric coefficients don't matter. We would write copper 2 is reduced to copper 0, and the potential is plus 3.34 volts. If I doubled this, having 2's here, the reduction potential doesn't change, right? It doesn't depend on how much is there. So the potential is just the same. Standard on the table, any species above and to the left will spontaneously react with anything below and to the right. It's called the diagonal rule. We'll see this more in a second. The strongest oxidizing agents are above and left. The strongest reducing agents are below to the right. Let's think about that. Remember, oxidizing agents want to be reduced. So anything that really wants to be reduced is a good oxidizing agent. Okay, let's think about the other way though. This guy, lithium, so let's think about the reverse reaction here. I'm going to write this. Lithium solid goes to lithium plus an electron. This is the oxidation half reaction, right? It's the reverse. So really what this potential becomes is the oxidation potential, and I want to know how much it wants to be oxidized. So I change the sign. So of this, lithium, of all the products, which would be the reactants in the oxidation reaction, lithium wants to be oxidized the most. Magnesium wants to be oxidized, but not as much as lithium. This is how we read this. Note that we write the plus. So we know, for example, that this means plus 0.34, but when we're doing electrochemistry, we put the positive on there to emphasize.